Thank you, Luke. So can everyone hear me? Okay, good. Well, first, thank you, Luke, for giving me this opportunity to talk about our research here. And so I'm Ying Wu from KAUST, and as Luke mentioned, I've been here for 14 years. So today I'm going to talk about the so-called double zero index materials. And before that, I would like to just briefly summarize what we are doing here. So basically, we have two different approaches. One is physics-based models, and we did this double zero index, acoustic Purcell effect, metasurface, and space-time modulations. And recently, we also developed into the data-driven approaches using the machine learning method to achieve different type of functionalities of metamaterials. But today I will focus on these double zero index material, which we had been working for quite a while. So first, I would like to give you some introductions about these double zero index materials. So if we look at this Maxwell equation as example, and we have four equations, and basically from these two red ones, we can derive the wave equation. And we notice that there are material parameters characterizing the material and which provide the link between the displacement field and electric field and also magnetic fields. So the refractive index is a square root of the product of them. And therefore, actually, we can have this parameter space expanded by these two parameters. And if you can look at these refractive index, if both of them are positive, then this n is positive. So this is a common dielectric material which support wave propagation. And similarly, if both of them are negative, and this is the left-handed material, the n is also a real number, but it's negative. So it also support wave propagation. But if they are of opposite signs, and then n becoming imaginary, and if n becoming imaginary, then the wave vector is also imaginary, and then the wave becomes evanescent. So therefore, I put red color, indicating that wave cannot be propagating, but rather evanescently decaying. So this quadrant means the metal, and this is some magnetic materials. So actually, now the question is, what happens if on the axis, like on the vertical axis indicating the epsilon is near zero or close to zero, and on the horizontal axis, that means the mu is near zero, the magnetic permeability is near zero. And also for acoustic waves, we can have an acoustic version. That means the 1 over Bach modulus equals to 0 is equivalent to epsilon equals to 0, or mu equals to 0. Rho equals to 0 means the density equals to 0 is equivalent to the mu equals to 0 case in the electromagnetics, because acoustic wave and electromagnetic waves, they have certain correspondence in two-dimensional geometries. So, and this, if we have one of the parameters becoming 0, we call it the single zero material. And what is more interesting is if what happens if we are on the origin, where both parameters becoming 0, and we call it double zero material. And actually, zero index material, when you have the refractive index nearly 0, that means the wavelength is infinitely large. And if we look at this picture that shows a reflection and refraction on a interface between a zero index material, which is highlighted in yellow, and a common material outside of this zero index material. By using the Snell's law, we can easily get that any incident wave angle outside from this zero index material will be reflected. And if you have normal incidence coming from out and it will be coupled into the wave, actually you don't have any direction. Any direction is okay. And if you have an incident wave coming from the zero index and outgoing wave must be perpendicular to the surface. So this is some features of zero index in terms of reflection and refraction. And now the question is, why we want to study this material? Because they have some intriguing properties, like here, the energy squeezing and tunneling. So you have, for example, you have a waveguide and connect two waveguides connected by these very crazily shaped narrow waveguides. But if you have normal material, there's no way that your wave can propagate from this waveguide to the other. But with zero index material, then this is possible, that you can squeeze the energy into these thin channels and then propagate. You can see there are some examples. And also wavefront shaping illustrated here. And here you have a this strange shape zero index material in green, and you have the plane wave incident from the left, and outgoing wave, as I mentioned here, the outgoing wave must be perpendicular to the interface, so therefore you can see some kind of focusing effect here. And also very recently, earlier this year, people have demonstrated that zero index can be used as an antenna, which has a very high directivity emission, and also anonymous tunneling in zero index materials. And also, this particular material has drawn some attention from the mathematics community. And Bob Korn and his collaborators published a paper earlier actually it was last year, and on the analytic analysis of the dielectric permeability in an epsilon near zero material. Actually, according to one of his talks, and they are also exploring the double zero index materials. So these are some general background. And now the question is, how can we achieve these special zero index material? Actually, the Mother Nature doesn't give us this type of material. And in the literature, there are two prevailing methods. One is called photonic doping, where you have a epsilon near zero material, and then you put some dopant and to actually make this double zero. And also, there's another way where we use the simple periodic structures. Here, you can see it's a square array of dielectric cylinders in air, and just a very simple photonic crystal. And people find that if you can make these so-called monopole mode and dipolar mode degenerate. So here at this point, you can see this is a dispersion relation. At one frequency, we have three modes degenerate at this frequency, and these three modes corresponding to these three modes here. So if you can have the dipole mode and the dipole mode, two dipole modes and one monopole mode degenerate, then you will have these so-called zero index property. And in a effective medium, using an effective medium model that I developed almost 20 years ago, we can exactly calculate at this frequency the effective epsilon and effective mu go across zero simultaneously. So then people adopted this idea to different type of systems, including acoustic systems, thermal system, and optical systems. So they all borrow this idea and using the degeneracy of monopole and dipole resonances. And by the way, because the lattice structure is a square lattice, so the X component dipole and Y direction dipole, they are degenerate because you cannot distinguish X and Y. And now the question is, how about the three-dimensional double zero index material? So what I have talked up to now are all limited in 2Ds. And we asked ourselves, how about three-dimensional? And if you want to make some like devices and materials, and we increasing the dimensionality would also bring you more functionalities. So here comes our first design in acoustic. For acoustic wave, actually we tried different type of like isotropic scatterers, but we found it's very difficult to find proper material and geometric combinations to give you the condition that you have dipole and monopole mode overlapping. And then me and my postdoc, we studied some literature and we found maybe we can just not stick us to only isotropic material, but rather think more about the geometries, the symmetry. So we apply this glide symmetry, and you can see there are three hard objects. This background is in the air, and we use these steel rods. You have three rods here satisfying the glide symmetry. And for a more symmetric view of the unit that looks like this, you have a very you can consider you have a volume of air in the center and then connecting to its neighbors. And we found that such kind of dispersion relation for certain geometry, and this is a single monopole mode, and this is a triply degenerated dipole mode, and their field distributions are plotted here. This is a monopole, and these three are dipole because this is a 3-dimension. So we have, and also in cubic lattice, so X, Y, and Z directions are identical. And then this actually gave us some hope because these are very close. And if we alter the geometries, and we can change the frequencies. And indeed, for a certain geometry, that the ratio of these rods and also the lattice constant, we found that indeed these four modes degenerate. And then for this structure, we cannot apply the effective median that we derived 20 years ago. That is for isotropic scatters. And for this complex unit cell, we developed a effective median based on the single mode approximation. So we read out these eigenmodes and did the field average, do the integrations of the field on the boundary, and then take the average. And then by applying their physical definition of each parameters, and we got the effective density and effective compressibility, which is the inverse of the Bach modulus. And we can find that for this geometry, where your L equals to this ratio of the lattice constant, then at this frequency, both the density and the compressibility passing zero at the same time. And then we did some numerical simulation and also performed experimental measurements that we put a banded waveguide and filled with this zero index material. And this is the effective medium, the very perfect case. And this is using our photonic crystal. It's a realization for the effective medium. And we have the incident wave coming from the top, and we measure the outgoing wave from these outlets. And we can see that with the zero index material, the incident wavefront is largely preserved. But without that, then the wavefront is heavily distorted. And this is a picture of our experimental setup. And we put these steel rods, assemble them together, and then did the experiments. And we measure the different fields, and then actually did a Fourier transform and see indeed at this frequency, the zero index frequency, we have a very small spot. That means your K equals to 0. And away from that, we have a gradually increasing Ks. So this is a demonstration or proof of our zero index property. And this is the field measured at the output plane. You can see they have still preserved the plane wavefront. And then we extended this to the electromagnetic waves. So I said at the beginning that acoustic waves and electromagnetic waves, they are mathematically equivalent, but just in 2-dimensional case. So for 3 dimensions, one is scalar wave and the other is a vector wave. So they don't have like really the mathematical mapping, but some features we can still borrow. So extended into the 3-dimensional electromagnetic wave, just to make the long story short, we find this type of structure that can give you the degenerate modes. But in this case, in the electromagnetic wave, we don't have monopole in 3D. And what we need to do is to have the electric dipole, the threefold degenerate electric dipole, and threefold degenerate magnetic dipole overlapping. That means we have to have 6 states degenerate at this frequency. And this could be achieved by altering, again, the geometric parameters. And then also by applying a similar effective median approximation based on the single mode approximation, we can calculate that the effective epsilon and mu passing through 0 at this frequency simultaneously. And we also perform this tight bending model analysis, trying to study these slope near the degenerate point or near this 0 index frequency. We want to see if we can see we have a cross and a flat band. But these 6 modes, we want to understand, well, how did they approach each other? So we calculate the slopes, and we found that there is a flat band in the vicinity of this 0 index point, and the rest 4 are linear bands, and 2 of them have the same slope, and the rest 2 have the same negative slope. So that means actually we have the so-called the double Dirac cone rather than 2 Dirac cones. So the Dirac cone is a linear dispersion, and double Dirac cone means that we have 2 identical cones, but like 2 Dirac cones means their slopes can be different. And then we also perform some experimental measurements to showcase some interesting features. Like here, we achieved this switching effect that you have, for example, like a double 0 index material in the center, and by applying the proper boundary conditions on this waveguide, and we can either achieve there is a total transmission at the back or 0 transmission. So here you can see this is the simulated results, and these are the experimental results. They agree with each other very well. So this is for total transmission case, and here is for the blocking case. And we can also do the redirection by removing one side, and then the wave coming from this side will be totally transmitted along the other, and also this case. So this is with the double 0 index material. You can see the wavefront are nearly not disturbed, but without the double 0 index material, then there's no wave can propagate. So this is a reference. And then at the end, I want to introduce some interesting feature about the doping effect. So in 2-dimensional case, for both acoustic and electromagnetic waves, if you put a 0 index material inside a waveguide, and then inside this 0 index material, you put some kind of impurities, and then we found that the transmission depends on this impurity. So this is the edge field along the boundary of this impurity, and then you take the integration on this boundary, and then you sum up all the possible defects, and then this transmission depends on that. So that means if you have different geometry, different numbers of impurity, your transmission will be different. So this is an example for, like, I have the same size of the impurity, but they have different dielectric constant. So either the waves are totally reflected or totally transmitted. And for 3-dimensional acoustics, we have a similar behavior that the transmission depends on you doing the surface integral of the field on the boundary of this impurity, and then you sum up. So this means that the transmission, again, depends on the size and the property of the impurity. But however, so this is an example that you either have total transmission or partially transmission. But for 3-dimensional electromagnetic wave, this is quite different from the previous 2 cases. So this transmission only depends on the intersections of the impurity of or projection of the impurity and with a true surface selected in this material. So these two surfaces, the A1 and A2, A1 should be cutting through the top and the bottom surface, and A2 cutting through the front and back surface. So as long as your impurity does not have any intersections with any one of them, so you can see this means the intersection. So if there, or in other way, if there exist these two surfaces that is not intersecting with any of these impurities, then your transmission is always 1. So that doesn't depend on the geometry or the material of your impurity, as long as your impurity is not connecting the top and bottom surface or the front and back surface. So here you can see we put very strange impurities and the transmission is always 1. And here, even this impurity, it's penetrating the front surface, but it's not connecting to the back. So the transmission is also unit. And also using these geometric or consideration or the symmetry considerations, we designed different type of this zero index material and add some flavors, for example, adding the absorption and the gain to make it a non-Hermitian. And we have these so-called complex conjugate medium to achieve these super absorption and lasing effect. And this is a super anisotropic double zero index material, which can hide an object inside this cavity. So today I don't have too much time to go into the details of them. If you're interested, you can refer to these publications. So let me sum up. So we achieved the double zero index materials for both acoustic and electromagnetic waves in 3 dimensions. And we have demonstrated some of these zero index features, but I have to say that these properties demonstrated is just a part of those intriguing properties. And like the acoustic periscope and the electromagnetic switching and redirection functionalities. And we reviewed different cloaking features or these doping effect. We found that actually this doping is quite significant in the 2D and 3-dimensional acoustic case, but it's not very sensitive in the 3-dimensional electromagnetic case. Yeah, so I hope I'm on time.
Thank you, Ying. That was excellent talk, fascinating stuff, and very good timing. We have a couple of minutes for questions from the audience. Audience members, if you would like to ask a question, best to put your camera on, perhaps put your hand up and I'll look out for you. I am happy to ask a first question if people need a moment to think of a question themselves. Okay, so Ying, can you explain to me a little bit the process that goes into coming up with one of these structures?
You mean like these?
It's fantastically complicated structures.
That's true.
You know, you sit down with a blank piece of paper, and you've got to come up with one of these things. What do you do first?
Actually, this is a long journey. So you can see in 2-dimensional case for these simple photonic crystals, this was achieved almost 15 years ago in 2011. So the paper was published in 2011, but actually I was not part of this paper, but I was involved in a lot of discussions with the authors of this paper. So this in the design, this actually at the beginning we were thinking of very complicated like core shell structures, but then at the end one day when we read some reference book and we found actually the structure can be very simple. So then starting from here, we want to design the 3-dimensional case. So the key ingredients, what we want, as I mentioned, is to have the monopole eigenstates and the dipole eigenstates degenerate. Why do we need this? Because the monopole states is associated with the effective epsilon, and the dipole states are associated with effective mu. This has been reviewed in our effective medium paper published in 2006. So at the end of the day, what we want is to make this monopole and a dipole meet. So if you just have a like random this photonic crystal in this case, of course you will have a monopole mode. This solution will you'll have these periodic conditions, and you will get an monopole mode for sure. And you will also get a pair of dipole mode for sure. But usually they don't happen at the same frequency, so they don't meet. And to make them meet, you have to adjust the size of the cylinder, and you have to adjust the material parameters. And we also want to adopt the same design into three-dimensional case. We tried concentric spheres, we tried different spheres, and we found that actually it's quite difficult because we indeed find some theoretically, but not practical, that with very strange material parameters, that we can get these degeneracy for 3D. But this is not practical, and also this degeneration is very narrow band. So that here, I'm not saying this one point is broadband, but you can see the dispersion that you only have these structure this states inside this Brownian zone, that you don't have any additional strange states there. But for our three-dimensional at the beginning, if with this sphere geometry, then in addition to this type of degeneracies, we'll see a lot of flat bands and other bands that also deteriorating this effect. And then actually, we were at that time, so this was published in 2020. So we actually tried a lot but failed. And then we were reading some paper on these topological physics, where this gives a lot of this geometry. If you have lattice satisfy certain kind of symmetries, you will have a certain type of dispersion. And then actually we read one day about this glide symmetry. So glide symmetry means that you rotate and shift. So you have these, and then you rotate by 2 pi and then shift to a distance. So this glide symmetry, we found that there will be some kind of interesting dispersion happening. It was not really this about the zero index, but for topological physics. And then we found this one. You can have a more symmetric view like this as the unit cell. And if you look at this unit cell, you found there is an air cavity inside. Okay, air cavity inside and connected by to the outer space. And also, like you imagine you have periodically put there, so you have a number of these air cavities and then connected to its neighbors. So also, again, bear in mind that we need to have the dipole resonance and the monopole resonance degenerate. So this, if you consider an air cavity inside, that will facilitate the dipole monopole resonance. Okay, and you change the size of this steel, then you can also change the frequency of the monopole resonance, and then the dipole will happen also as well. But this one is we found that by fine tuning it, we can tune them together. So to find this structure, I have to say this is not a easy journey, but it's we also were studying topological physics, and we know that some kind of lattice symmetries will give you some particular band dispersion, and also combining the purpose that we want to have the dipole and monopole degenerate. So how to like make the dipole and the monopole like more sensitive to when you adjust the material parameters. So we eventually found this structure is the best.
Okay, thank you.
There might be other structures, I have to say, but we didn't find that.
I can see that Eric has his hand up, and as you can't hang around until the end, I'm going to let Eric ask his question. And also, it's a tradition, of course, waving after run a few minutes behind. Go ahead, Eric.
Yeah, I'll be very quick. Thanks a lot. First of all, Ying, that was very fascinating. I just wondered if you could say a couple of words about dissipation, because I know from the acoustics community that often all these kind of perfect transmission effect and so on, some of the papers that you mentioned in the beginning, once you include thermoviscous losses, that doesn't really happen. But you did show some experiments there where you could see it. So I wondered if you could say just a couple of words about, all these losses and whether the experimentalist people have suffered with those and how kind of it translates into electromagnetics as well. Is it an issue? Is it not? The experiments look really good, but I wonder if you could say a couple of words about that.
Okay, certainly. So this is a very great question about these dissipations. So that's why actually when we were doing this this electromagnetic experiments were performed in the microwave. So for the microwave, the dissipation is not that significant. So therefore, we can observe this property. But if you go to the optical waves, then it's quite challenging. And that's actually, if you can see here, I have introduced this reference published at the beginning of this year, and they were using some very high dielectric constant material. So actually, if you use metal, then this in the optical frequency, then this loss is unavoidable. And I have to say, these loss also, like about this robustness of zero index property, really depends on how much loss that you have. So if you have a little loss, it's fine. You can still observe some like properties, just like we did in these microwave experiments. By the way, I didn't do that. It's my collaborators did that. So certainly in the system there is loss, but it's not that significant. But if you have really big losses, will smear out these features. Yeah.